Hey everybody, welcome to the second video in Class 9. This one's called Generating Electricity from Wind and Sun. And we've really laid the groundwork for how wind is created, how solar insolation varies, and what we're going to do now is have a short video about how we actually harness electricity from both the wind and the sun. Now, who cares about this? It's important to understand how the electricity is actually made, because that's what governs the efficiency of wind and solar energy, and also the footprint, so how much area each technique requires. So I don't have an outline for this video, we'll just jump right into it. One of the basic things you need to know, and this will also come up in lab, is units of electrical generation. So if you want to talk electricity, what's the language that we speak? A very common term is watt. That's a rate of energy expenditure or a rate of electricity generation. So it's a rate of energy going in or out of something. Now, a watt hour is what you get if you produce that rate of energy for 1 hour. So you produce energy at a watt for an hour. That's a watt hour. Okay, so for example, imagine, well actually first let me give you one more piece here. So whenever you talk about energy installations like a solar farm or a wind farm, usually it's installed with what's called a nameplate capacity. So that's the total power that would be produced if all the wind turbines or solar panels ran at peak output all the time. Okay, so basically let's consider a wind farm. You might have a 2.5 megawatt turbine. That's how much it makes at its maximum output. But if the wind's only blowing half strength, you're only going to get half or less of that maximum. So the nameplate capacity is what it would produce if it ran at maximum all the time, but of course it doesn't do that. And that brings in the capacity factor. So the capacity factor is the ratio of the actual production over the nameplate capacity. So for wind, that's usually going to be 30 to 50%. Wind in Vermont, of course, would be much closer to 30%. 50 would be very high. So let's work through an example here. So imagine you have a 2.5 megawatt turbine. That's its maximum production. But it only produces an average of 1 megawatt. Okay? And now it does that for 8760 hours, or a year. Then it would have produced 8,760 megawatt hours per year. Okay, so each year it produces 8,760 megawatt hours on average. So what would the capacity factor of that be? It would simply be its average generation of 1 megawatt divided by its nameplate capacity of 2.5 megawatts. So it would have roughly 40% or 0.4 capacity factor. So we'll be using all this stuff in lab. So now let's move into thinking about how electricity is actually generated. Most electricity is generated by spinning a turbine. Literally, the way this works is that there's an electromagnet that is a bunch of copper wire spinning in the vicinity of a magnet, and when it spins, it generates an electrical current. So you have to actually spin this physical ball of metal or ball of magnetic material to generate a current. So wind is pretty nice because the blades of the turbine are directly attached to that generator. We don't have to make steam or anything like that. They're just directly attached through a set of gears, and they spin it. Now, obviously, the faster the wind blows, the faster that thing spins and the more electricity we make. And so this plot shows basically the power output as a function of wind speed for, I think this is a 2.5 megawatt turbine. So yes, it is. So in order to even spin the turbine, the wind has to be blowing about 4 meters per second. That's reasonably fast. And then we see that as that wind speed increases, we quickly ramp up our production. And then we top out at around well, 2.5 megawatts. And notice that there's usually a cutoff speed. So if the wind goes above a certain speed, like 20 meters per second, or in this case maybe less, it's unsafe for the turbine to operate, so it will actually shut down in very high winds. Now, if you want to estimate how much electricity a turbine can make in a given year, of course you need to know how much time in the year, what fraction of the year, the wind is blowing at each of these speeds. If the wind is always blowing at 10, well, you'll make quite a lot. But if the wind's only blowing at 6, you'll make a lot less. So one of the ways that the wind industry predicts this stuff is by using what's called a Weibull function. So I'm showing that here. The x-axis is wind speed, and the y-axis is the percent of year that the wind blows at a given speed, or the fraction of the year. So what this shows is that if you know the mean wind speed, let's say 9 or 10 meters per second, you can use this Weibull distribution to predict the fraction of time in the year that it blows at all these other wind speeds, higher and lower. And it turns out that most places on Earth, the distribution of wind speeds follows this Weibull distribution, and so it can actually predict that distribution pretty accurately. And then you could go on to estimate how much electricity you're going to make at each of these different wind speeds over the course of the year. So what about spacing of wind turbines? How close can you put them together, and how much space is a wind farm going to take up overall? So this picture of offshore wind turbines in a fog shows a pretty important concept, and that is that wind turbines generate turbulence in their wake. And we already talked about that in the last video. So the wind's coming in as laminar flow, and then it gets disturbed. What that means is that the turbines behind it the wind's not going as fast because it's been slowed down by this turbulence. So we need to space out the turbines so that the wind can kind of recover and pick up speed again, and so that these turbines don't suffer too much in each other's wake. So depending on a bunch of factors, turbines would typically be spaced 3 to 10 blade diameters apart. You can see these look like they're closer to 10 blade diameters apart. And the exact pattern of turbines depends on a bunch of factors also, like which direction the wind's coming in, and of course what the topography is like. And so picking up on that idea of topography, let's take a quick look at where wind turbines would go if wind was developed in Vermont. Okay, so this again is a map of mean annual wind speed in Vermont, and we're here in Middlebury. And what stands out here in blue and green is the crest of the highest peaks of the Green Mountains. Okay, those are where we get the really good wind speeds, class 5 and 6 here. And of course those are on ridge lines, and here's a blow up of that. This is the Bolton Stowe area. So here's Bolton Mountain, and then this is Mount Mansfield where Stowe is, and then this is Madonna Peak where Smuggler's Notch is. So if you were going to propose to develop wind in Vermont, you'd need to put the turbines in strings, actually. Linear features shown by these black lines that would actually be kind of strings, or rows of turbines that would just be right on the ridge crests of the highest mountains. And obviously the wind speed just isn't high enough anywhere else in Vermont. So that obviously creates some issues for people who really value protecting the highest peaks in Vermont and don't want to see wind developed up there. And it's made it a pretty contentious issue in the state. So just in summary, wind has some amazing benefits. Has a very low carbon footprint, it's completely renewable, has relatively few long-term environmental impacts. Basically, you can take those turbines down and the trees will grow back probably. It's also a benefit because it's distributed electrical generation. It's electricity that may be made near where people need to use it. But there's also some problems. It has a very large spatial footprint, and at least in Vermont, a lot of issues with building big turbine arrays on top of our highest mountains. Another issue is it's not super reliable. The wind doesn't always blow, which means it can't be counted on for what's called base load, or that's the electricity that you need to have all the time, nor can it really be counted on for peak demand load. So you can't turn it on by flicking a switch when electrical demand is peaking. And importantly, it also requires a lot of new infrastructure. So in addition to the turbines themselves, you got to build roads up to them, you got to build power lines and clear cuts to connect them to the grid. So some pros and cons for wind energy for sure. Okay, so let's switch gears now and look at how electricity is made by solar panels. And this is done using what are called photovoltaic solar panels. And here's a pretty simple diagram of one of those. It's basically a material that's made of two different semiconductors, a p-type and an n-type. And you don't really need to know what those mean. The main point is that photons from the sun come in and they interact with electrons in the p-type layer, and they impart their energy to those electrons and allow them to mobilize and travel up towards the surface of the solar panel, where they're then drawn off by a voltage along an outgoing wire. So they then go through this wire. They are able to make electrical power, and then the electrons flow back in to the P layer from the backside, replenish those holes, and they can actually then be bumped up again by another photon. So basically you've got this flow of electrons going out and then coming back in, and they're constantly being bumped from one layer upwards by photons. So obviously we need sunlight to power this process, but it turns out that you don't actually need direct sunlight. Obviously, solar panels can still make electricity on a cloudy day. So let's look at how that works. We can think of the sun's radiation in terms of two components. One we'd call direct radiation. So those are photons that come straight from the sun and hit the solar panel. And then the second component is called diffuse radiation. Those are photons that come through and they have some interaction in the atmosphere. They get scattered off of molecules of gases, and they end up being scattered in all different directions. But of course, some fraction of those end up going down and also striking the solar panel. So the important thing is that on really cloudy days, there's a lot more water vapor in the atmosphere, and that ends up scattering the light really badly. So that's why on a cloudy day you can't see the sun directly, but it's still light out because we're still seeing based on this diffuse radiation. So needless to say, you're going to make a lot more electricity if you can harness the direct radiation from the sun than if you have to rely on the diffuse radiation. But nonetheless, both of them contribute. So to finish up here, what do photovoltaic panels look like? Obviously you know what they look like, but there's three main types. There's a fixed tilt, where you basically bolt them to your roof and they don't move. So with these, you got to pretty much choose an orientation that's going to get you the best overall solar exposure. Other types are a single axis tracker, where they're able to rotate forward or back along that single bar. So those can adjust a little bit to better square up against the sun during different seasons. And then finally we've got the two-axis tracker. So these of course can rotate 0 to 360 in a compass direction, but then can also change their vertical angle. And these of course can perfectly follow the sun, and they're going to give you roughly a 35% increase in your energy yield relative to a fixed tilt panel. So the benefits of solar electricity in general are very similar to wind. One major benefit over wind, in my view, is that solar can capitalize on existing surfaces in developed areas. So that includes rooftops, parking lots, whatever. You can put them on stuff that already exists. They don't necessarily need their own dedicated space. And in general, some drawbacks of solar, especially in Vermont, are that it has a big spatial footprint. So it takes a lot of space to get those panels out there. And again, it's not as reliable as most other centralized electrical generation. And we'll explore these trade-offs in lab this week. So I'll leave you one concept question here. Here's a link to a quiz for this video. And see you on Wednesday when we talk about geothermal energy.